All right, so here in chapter 13, we are going to be taking a look at multivariable functions. Now, up until now, we've been looking at, when we're looking at scalar functions, where you have y as a function of x, right? Our entire existence through Calc 2, we've been, doing analysis of functions where we integrate, differentiate, take limits of, yada, 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 of y as a function of x, a function of one variable. Well, now we're going to pick up the pace and bump things up by one or more dimensions. So we're now going to start looking at a z, for example, as a function of x and y. Or maybe w as a function of x, y, z. So, in other words, functions where there are going to be two or more independent variables. Okay? So, all right, so let me get my pen out here. Let's see. I feel like green today, so what we're going to talk as our first topic about is planes in 3 dimensions. Now, the plane in 3 dimensions is analogous to a line in 2 dimensions. Now, remember what you needed to define a line in 2 dimensions was a point and a slope, right? Well, something similar to that for the plane. We need a normal vector and a point. The normal vector basically gives us a direction. What do we mean by a normal vector? Well, basically a vector that is orthogonal to any vector that lies in the plane. So imagine that maybe that you have this plane here, a section of the plane. Well, a normal vector would be where here is our normal vector, and of course any vector that is parallel with our normal vector is also going to be a normal vector. So any vector, call it P or something, that is in the plane that our normal vector is going to be orthogonal to. That's what our normal vector is. All you need is a normal vector and a point. Okay? So let's take a look here. Here's our plane, this little light yellow sort of 2-dimensional object in 3 dimensions, flat. And here's our normal vector, and let's call it its components A, B, C. Now, I told you we need a point. Call that point P sub 0 with the coordinates x sub 0, y sub 0, z sub 0. And then let point P be any other point on the plane with coordinates x, y, z. And what we want to do is to write an equation involving x, y, and z. So that the point P with coordinates x, y, and z satisfies some sort of condition. What condition is that? Well, the condition says that when P sub 0 goes out to P as a vector, that vector is orthogonal to our normal vector. So what is a condition for 2 vectors to be orthogonal to each other? Their dot product must be 0, exactly. Their dot product must be equal to 0. So what we do then is that we take the dot product of the vector that goes from P sub 0 to P with n hat, or m, or whatever. So take that dot product, set that dot product equal to 0, and you'll have the equation of your plane. So here's what that dot product looked like. Remember, our normal vector was A, B, C, and the vector that went from P sub 0 to P had components x minus x sub 0, y minus y sub 0, z minus z sub 0. So when you take the dot product, you have this expression right here. See, the dot product is set equal to 0. So now, if you are given your normal vector, a normal vector, any normal vector will do, then write the components of your normal vector for a, b, and c, and then write the coordinates of that one point that's on the plane for x naught, y naught, z naught. Throw them in there, simplify that algebraic expression, and boom, you've got the equation of your plane. Of course, when you multiply all this out, you'll have a times x sub 0, actually a minus a x sub 0, minus b y sub 0, minus c times z sub 0, which then you can add them all over to the right-hand side. You have some number, and then your plane will have this sort of equation right here. Now, just like in standard form, our line in 2 dimensions would have the equation in the form ax plus by equals d. Well, then we have a new dimension for a plane. Now we have some constant times z. So do you see the analogy between planes in 3 dimensions and lines in 2 dimensions? And of course, different points, but with the same or parallel normal vectors, will just adjust the plane in 3 dimensions. So, meaning, look, if you've got the same normal vector, but you have different points that would lie on the plane, separated in 3 dimensions, then you would have parallel planes. Planes would be parallel if they have normal vectors that are parallel with each other. Regardless if they are the same plane or not, they could go 3 different points and be parallel with each other, as long as their normal vectors are parallel. Okay, let's do an example here. Let me pull up my textbook here. Section 13.1, example number 1. All right, example number 1. So we have a point P sub 0 with coordinates 2, negative 3, 4, and a normal vector, negative 1, 2, 3. What is the equation of a plane that contains this point, P sub 0, and has a normal vector of negative 1, 2, 3? Well, that's easy. All we need to do is just use that formula that said a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. All right, let's do that. Well, so the components of your n vector will be the coefficients for x, y, and z terms. So we'll have negative 1 times x minus 2 plus 2 times y minus negative 3 plus 3 times z minus 4 equal to 0. And now we just do the algebra to multiply using the distributive property each of these terms. Negative x plus 2 plus 2y plus 6 plus 3z minus 12 is equal to 0. Now we have the constant terms of 2 plus 6, which is 8, minus 12 is negative 4, so we can add 4 to both sides of the equation. So we'll have negative x plus 2y plus 3z is equal to 4. And we have the equation of our plane right here. Any questions on how we do that? It's basically plug and chug, right? You have your normal vector, you have your point, plug in the numbers, and chug away. So this is a picture of what we just did here. We had the point 2, comma, negative 3, comma, 4. And we had our normal vector, negative 1, comma, 2, comma, 3. And here was the equation of the plane that we just came up with. That's the equation of this plane here, this graph. All right, let's do another example. Now suppose that I simply tell you what is the equation of a plane that contains 3 points, and give you the coordinates of those 3 points, and what would be the equation of that plane if all you know is those 3 points. Well, what do you need to define a plane? You need a normal vector and a point. So if I give you 3 points, can you come up with an equation that of a vector? I mean, can you come up with a vector that is orthogonal or normal? Sure you can. It's called taking a cross product. So let's write down the coordinates of these 3 points. We have a point P, which is 2, comma, negative 1, comma, 3. We have a point Q with coordinates 1, comma, 4, comma, 0. And a point R with coordinates 0, comma, negative 1, comma, 5. So imagine that you have points P, Q, and R. And we're going to shoot a vector from P to Q, shoot a vector from P to R, and then the cross product of PQ cross PR will be your normal vector. Okay? So, the vector that will go from P to Q. Alright, 1 minus 2 is negative 1. 4 minus negative 1 is 5. 0 minus 3 is negative 3. And now shoot a vector from P to R. So 0 minus 2 is negative 2. Negative 1 minus negative 1 is 0. 5 minus 3 is 2. And now let's go ahead and calculate the cross product. PQ cross PR. So we have negative 1, 5, negative 3, negative 2, 0, 2. Now for I hat, we got 10 minus 0, so we have 10 I hat minus, and then for J hat, we got what? Negative 2 minus 6 is negative 8, so minus negative 8 is plus 8 J hat. And then for K hat, we got 0 minus negative 10, so we have plus 10 K hat. Now, any vector that is parallel with this vector can serve as a normal vector. Any normal vector will do. And notice that you have a common factor of 2 there, so you could use, if you want to divide out of 2, you could use 5I hat plus 4J hat plus 5K hat as your normal vector. Okay, does everybody understand what I'm doing there? Okay, and now we have a normal vector. Does everybody understand why this vector is our normal vector? Okay, anybody not understand? Okay, and then we could choose any one of these 3 points. Any point will do. Let's use P. So we're going to now write 5 times x minus 2 plus 4 times y minus negative 1 plus 5 times z minus 3 is equal to 0. Multiply out, use the distributive property, 5x minus 10 plus 4y plus 4 plus 5z minus 15 is equal to 0. So we're going to have 5x plus 4y plus 5z And then for the constant, we have a minus 10 plus 4, that makes negative 6. Minus 15, so that's minus 21. So add 21 to both sides. And then, boom, you've got the equation of the plane. Now, if we had 10x plus 8y plus 10z equals 4, we would still have the same equation. So if you have some other equation where, you have the same multiple on both sides of the equation, you'd still have the same equation of the plane. Okay? Any questions on how to do this? All right, so there's a picture of what we just did. So we had our 3 points, P, Q, and R. Took the cross product to get our normal vector. I took half of that, which is still a normal vector, and then used the formula to come up with the equation of the plane. All right, do another example. Number 3. Now, we are given the equation of a plane, 2x minus 3y minus z is equal to 6. And we've got some questions to answer. First, what is a vector that's normal to this plane? Well, all you need to do is to just take a look at the coefficients. You have the 2, the negative 3, and the negative 1. And those coefficients will be the components of a normal vector, 2, negative 3, negative 1. So any vector that is parallel, meaning a scalar multiple of this vector, will also be a normal vector. All right, part B, find the points at which this plane Q intersects the coordinate axes and plot Q. Okay. Now, we're going to be moving into the territory as we progress through this chapter of you have an equation involving 3 variables, and we're going to want to plot the graph of it. And how do you plot the graphs of these 3-dimensional objects? Well, it has to do with intercepts and traces, which we'll be discussing. For this particular sort of thing, we would get our intercepts by, setting pairs of variables equal to 0. So, for example, we could set y and z equal to 0. And solve for x. That'll be our x-intercept. So part B, you could set y and z equal to 0. That means that you have 2x is equal to 6. That means x is equal to 3. So 3 is your x-intercept. Meaning that in 3 dimensions, this plane is going to hit the x-axis at 3. Likewise, you could set x and y equal to 0, and then you would have negative z is equal to 6, which means that z is equal to negative 6. So negative 6 is your z-intercept. Also, you could set x and z equal to 0, which means that you would have negative 3y equals 6, which means that y is equal to negative 2. So, you have 3, negative 6, and negative 2 as your intercepts. Also, this is for part C of the problem, when you want to find the trace of the plane, which basically means if you set one of the variables equal to 0, what is the line that is traced out in the coordinate plane. So meaning, suppose that we set x equal to 0, then you'd have negative 3y minus z equals 6. That would be the equation of the line that would appear in the yz plane, where this plane intersects the yz plane. For example, so if you set x equal to 0, then you would have negative 3y minus z is equal to 6. That's the equation of the line on the yz plane called a trace. We'll talk about traces more later. Set y equal to 0, then you'd have 2x minus z is equal to 6. So in the yz plane, 2x minus z is equal to 6 is the equation of the line where this plane, our plane right there, will cross the xz plane. And finally, let z be equal to 0. So now we're on the xy plane. If you set z equal to 0, you have 2x minus 3y equals 6. So if you want to sketch the graph of this plane, you could do it. You could plot those intercepts, 3, negative 6, negative 2, and you could sketch these lines on the 3 coordinate planes, and then boom, you would have your plane. Now leaves a portion of the plane defined by the intercepts. So, for example, y equals negative 2, x equals positive 3, z equals negative 6. Those are your intercepts, which are points, right? The traces are where you have one variable equal to 0, and then you have the equation of the line or the curve in general in the appropriate coordinate plane. For example, this red line right here is where we had set z equal to 0. So you have 2x minus 3y equals 6 on the xy plane. So this plane, as it comes up through here and intersects the xy plane, that red line is the trace of that plane in the xy plane. For example, moving on here. Just real quick, unless two planes are parallel with each other, they're going to cross. The only reason they're not going to cross is that they would be parallel. So if they are going to cross, at what angle do they cross? What would be the equation of the line where they do cross, and so forth? We can ask those sorts of questions. They'll intersect at some angle. And in particular, what would it look like if they intersect at 90 degrees? And if they do, we would say that those are orthogonal planes. So here's kind of what it looks like here. You have orthogonal planes where they cross at 90 degrees. But how can you tell? Oh, folks, it's real simple, all right? Take a look at their normal vectors. And then take the dot product of their normal vectors. If it turns out that their normal vectors have a dot product of 0, that right there is a dead giveaway that those two planes are orthogonal to each other. If one normal vector is a scalar multiple of the other normal vector, then the two planes are parallel. And of course, if neither is the case, then they're neither parallel nor orthogonal. They will cross somewhere. It's just that they're not crossing at 90 degrees, and they're not parallel with each other. So that's what this says. There's this little blurb in the book that basically says the same thing that we just talked about. Dot products, scalar multiples. Otherwise, if you want to find the angle that they cross each other, all you really have to do is to take the arc cosine of the dot product of the two normal vectors, which we know how to do. That'll give you the angle at which those two planes intersect each other. Okay, no surprises there. And in particular, if the two normal vectors are parallel with each other, what will this give you? What will this quotient be? If N1 is parallel with N2. Taking the arc cosine of 0, right? And then what would it look like if they are perpendicular or orthogonal to each other? It would be 0, right? Because so the angle would be pi over 2 when the dot product is 0, right? 90 degrees. The angle would be 0 when the two vectors are parallel with each other, which means that so what would this argument for the arc cosine be when they're parallel with each other? It's not a rhetorical question. What do you think it is? Well, if you're not sure, draw a picture of the unit circle, huh? Here's the unit circle. Yeah, it's either going to be the arc cosine of 0 or 1, huh? Now, when you're at 0, you're over here at pi over 2, huh? And when you're at 1, the angle is going to be 0. And by the way, theta is going to be some angle between 0 and pi over 2. All right, moving along here. Take another example here. So, example number 4, they give us 4 planes. We have plane Q given by 2x minus 3y plus 6z is equal to 12. You have plane R, which is negative x plus 3 halves y minus 3z is equal to 14. We have plane S, 6x plus 8y plus 2z is equal to 1. And we have plane T, negative 9x minus 12y minus 3z is equal to 7. So we have 4 planes. Are any of these planes parallel with each other? Are any of these planes perpendicular to each other? So to answer that question, let's go ahead and calculate normal vectors. The normal vector for Q would be, just look at the coefficients for Q. 2, negative 3, 6. Normal vector for R, we have negative 1, 3 halves, negative 3. Normal vector for S, 6, 8, 8, and 2. And normal vector for T, negative 9, negative 12, and negative 3. Now, if you were to compare the normal vector for Q and the normal vector for r, and you'll notice that if you were to take negative 1/2 of the normal vector for q, you would have the normal vector for r. So the normal vectors for q and for r are parallel. That means that q and r are planes that are parallel with each other. So you take negative 1/2 of the normal vector for q is equal to nr. So that means that q and r are parallel. And same discussion with s and t. The normal vectors for s and t are, well, if you're to take half of the normal vector for s and take a negative 1/3 of the normal vector for t, then you'd have the same vector. So you could say that, I don't know, 1/2 of n sub s is equal to negative 1/3 n sub t. So you could write one as a scalar multiple of the other. You could write n sub s as negative 2/3 of n sub t. So that means that s and t are parallel as well. You could also check to see if any of these planes are parallel or perpendicular to each other, orthogonal to each other, by taking dot products. So, for example, if you were to take the dot product of the n sub q and n sub s, what would you have? You'd have 12 minus 24 plus 12 is 0. So this dot product is 0. But because of the fact that n sub q is orthogonal to n sub s, that means that n sub q is also orthogonal to n sub t. Okay? And also n sub r, then because n sub r is parallel with n sub q, it's going to be orthogonal to n sub s and orthogonal to n sub t. So because n sub q dotted with n sub s is equal to 0, so that would imply that q is orthogonal to s, q is orthogonal to t, that r is orthogonal to s, and r is orthogonal to t. Okay? Any questions about that? Moving along here, let's do another example. Parallel planes. Find an equation of the plane Q that passes through a particular point so it goes through a point P, negative 2, 4, 1, but parallel to the plane. So we want Q to be parallel. What's the symbol for parallel? Two parallel lines, right? So we want Q to be parallel with R, and that R is given by 3x minus 2y plus z is equal to 4. What was the relationship between normal vectors of parallel planes? They essentially have normal vectors that are parallel with each other, right? Scalar multiples or even the same. So we could use the normal vector from R and use it as our normal vector for P, or for R, I mean, or Q, I should say. So let's go ahead and use that normal vector, 3, negative 2, 1. So we have our normal vector, we have our point, and we can go ahead and write the equation of our plane. Now, x minus negative 2, which is x plus 2, plus negative 2, so negative 2 times y minus 4, and then plus 1 times z minus 1 is equal to 0. Multiply it out, 3x plus 6 minus 2y plus 8 plus z minus 1 is equal to 0. 3x minus 2y plus z. So we could subtract 6, subtract 8, add 1. So it means that we're subtracting 13 from both sides. So this then will be the equation of the plane that goes through that point P and is parallel with plane R. So this is our plane Q as requested. Any questions on how to do that? Now, you might be invited to find the parametric equations of a line, the line, that is formed by the intersection of two planes. So suppose that we got plane Q, plane R, and they intersect along a line. What would be the parametric equations for that line? Well, what do you need for a line? You need a direction vector and you need a point. Huh? So number one is find a point of intersection. Any point will do. And I'll show you how to do that. And the other thing that you'll need is a direction vector, right? So what do we use for a direction vector? And all you need to do is to take the cross product of the normal vectors from the planes. And the result of that cross product will be a vector that is orthogonal to both of those planes, meaning a vector that points in the direction of the intersection line. Does that make sense? So let's do example number 6. So we have a plane Q, x plus 2y plus z is equal to 5. And we have a plane R given by the equation 2x plus y minus z is equal to 7. Let's go ahead and get our normal vectors. N sub q is equal to 1, 2, 1. We need a normal vector for R. 2, 1, negative 1, negative 1. Go ahead and take cross product. N sub q crossed with n sub r. We have I hat, j hat, k hat. 1, 2, 1, 2, 1, negative 1. So for I hat, we got negative 2 minus 1 is negative 3 minus, and then for j hat, we've got negative 1 minus 2, which is negative 3 minus negative 3 is positive 3. And then for k hat, we got 1 minus 2 is negative 3. 1 minus 4 is negative 3. K hat, thank you. See, my mind works about 10 times faster than my hand. So does it look like it did that calculation correct? Got negative 2 minus 1 is negative 3. We got negative 1 minus 2 is negative 3. We got 1 minus 4 is negative 3. Okay. Now, you could use this vector here as your direction vector for your line or any scalar multiple. And in particular, you can use maybe negative 1/3 of it, like 1, negative 1, and 1. So everybody see what I'm doing? Just take negative 1/3 of this vector and I could use that as my direction vector. Hey, work with numbers that are as small and simple as possible, okay? Now, so we've got our direction point, our direction vector. We need a point, some point in the intersection. The technique that is usually suggested is to set one of the variables equal to 0 in both equations. Like, for example, z. Now, I can guarantee you that both of these planes are not parallel to the xy plane. Because if they were, you wouldn't see z in their equations. So both of these planes will cross the xy axis, or the xy plane, I mean, for which means that z is equal to 0. So you set z equal to 0. So set z equal to 0. And then you have for q, your q plane, you have x plus 2y is equal to 5. And from your r plane, 2x plus y is equal to 7. Two equations, two unknowns. It's a simple algebra problem, right? So use your favorite method for solving a system of two equations with two unknowns. So for example, we could take 2 times the first equation minus the second equation. So we have 2x minus 2x is 0. We have 4y minus y is 3y is equal to 10 minus 7 is 3. That means that y is equal to 1. Plug that 1 back into either one of these equations. Maybe the second equation here, y is equal to 1. That means 2x is equal to 6. That means x is equal to 3, right? So we have a point of intersection. We have 3, 1, 0. We have, that is one of many, many points on the intersection. In particular, this point is going to be where that intersecting line crosses the xy plane, where z equals 0. Any point on the intersection line will work, but this is just one. We didn't have to set z equal to 0. We could have just as well set y equal to 0 or x equal to 0 and got a different point on the intersecting line, and it doesn't matter as long as it's on the line. All right, so we've got a vector v here, and we've got a point. So now we can do our parametric set of equations here. So let's see here. X of t is equal to 3 plus t. Y of t is equal to 1 minus t. Z of t is equal to 0 plus t. And of course, t is the set of all real numbers. So there's our parametric set of equations to define a line that goes through the intersection, that is the line at the intersection of those two planes. Any questions of how we did that? So how did we get that direction vector again for the line? Which is the cross product of the normal vectors, right? And how do we get our point? Yeah, we just set a variable equal to 0 in the two equations, and then we solve for the other two variables, right? Okay. All right, let's take a 10-minute break. We'll come back and we will continue this discussion of multivariable. And can you push that door all the way open and prop it open with that cinder block, please? Because it's getting really stuffy in here. And folks, it's only going to get worse as the summer wears on. So, okay. So we're going to now start talking about surfaces in 3 dimensions. And our first little subtopic here is what is a cylinder in 3 dimensions. Now we all have an idea of what a cylinder is. It's like the shape of a pop can, right? Just basically, you know, a circle that's expanded in a 3rd dimension linear-wise. That's our ideal of a cylinder conventionally, but here is another definition of a cylinder. I'll show you a picture here in a minute. But we have some C, that's some curve C, I should say, that's in a plane P. So imagine some plane P, it could be at some weird angle or whatever. And then we have some curve that lies on that plane. And then imagine that we've got some line that comes up through that curve at whatever angle, whatever. So you've got a curve and a line that goes through that curve. And then imagine the infinite collection of all the other lines in 3-dimensional space that are parallel with that one line that goes through that curve. And the result is a cylinder. So for example, this is a cylinder. This red curve right here is a curve that could lie in some plane. And we have some line, maybe this one right here, that goes through that curve C, intersects that curve at that point right there. And then the cylinder consists of the collection of all the other lines in 3 dimensions that are parallel with L. And then the result is you have this surface in 3 dimensions. Now typically we have our cylinders that are parallel with one of the coordinate axes. Like for example, in this one right here we have this cylinder that's parallel with the x-axis. So when we look at the equation for the surface, we would not see the appearance of the x variable in that equation. It would just only involve the other 2 variables, x and y. Y and z, I mean. Y and z, for example. Some other cylinders here. This first cylinder on the left is the cylinder with the equation y equals x squared. That is parallel with the z-axis. In particular, when z is equal to 0, you have y equals x squared in the xy plane. But for all other values of z, y is equal to x squared. So z is arbitrary. Regardless of what z is, y is equal to x squared. So z could be 100 or negative 1,000, whatever. But you still have the trace of a parabola defined by y equals x squared. This cylinder right here, we have y equals z squared. It's parallel with the x-axis. So you won't see the variable x in the equation that defines the surface. And of course, if we had a cylinder that was parallel with the y-axis, then we would see an equation involving only x and z, for example. So if you have an equation and you know from the context the problem is involving 3 dimensions, and you need it to graph it, then you will just go ahead and graph the one curve. Like for example, y equals z squared, just graph the curve on the yz plane, the graph of that equation, and then graph several copies of it in the positive x and the negative x direction, and then just sketch several construction lines that are parallel with the x-axis, connecting those parabolas, for example. And you'll have your surface. Now, it's a shame that this is not a computer-based class, because I would love to have you guys do some exercises on Maple or MATLAB or Mathematica or in some other computer algebra system. We're just not set up for that in this school, but you could if we wanted to, though. You could, if you're familiar with any of those computer algebra systems, you could. Also, if you have TI-89s or HP-48 or some of those high-end graphing calculators, you can graph surfaces on your calculators too. But it's not a requirement. The big requirement is for you to think about these things in 3 dimensions, is to visualize in 3 dimensions. That's the important thing. The best computer algebra system's right here in your head, between your 2 ears. Let's talk about what a trace is. I've mentioned that a couple of times, and here's the official definition of what is a trace. And it really comes down to this. You have some equation involving x, y, and or z, which is the equation for a surface, the surface being the graph of that equation involving 3 variables. And what the trace is going to be, in essence, the intersection of that curve with one of the 3 coordinate planes. So if you were to set x equal to 0 in that equation, then you would have an equation involving y and z, for example. So you would be having an equation of the trace of that surface in the yz plane, for example. Or if you were to set z equal to 0, and then you would have an equation involving, only x and y, and that equation being the trace in the xy plane, otherwise known as the xy trace, etc. So when it comes to graphing these surfaces, and you have your equation involving x, y, and z, how do you graph it? Well, if you're doing it by hand, then you will find your x, y, and z traces. Sorry, your xy trace, your xz trace, your yz trace. Also find your intercepts by setting y and z equal to 0, solve for x. Set x and y equal to 0, solve for z. Set x and z equal to 0, solve for y. So intercepts and traces. Intercepts and traces, that's all you need in order to at least get some hint as to the shape of your surface. Oops. So let's take a look at this. This is figure 13.10, where we've just got this paraboloid here. The xy trace for this is where you see is equal to 0, and that trace is going to be some ellipse or maybe a circle. The yz trace would be where you set x equal to 0, and you got some parabola in the yz plane. And here we set y equal to 0, and then you have this parabola in the xz plane. So using those 3 pieces of information, you should be able to discern that, okay, you've got this ellipse here, you've got this parabola here, you got this parabola here, and then, hey, you've got a paraboloid. 3-dimensional version of a parabola. All right, here we've got, for example 7. Example 7, for part A, we've got x squared plus 4y squared is equal to 16. Here's the equation right here, x squared plus 4y squared is equal to 16. You don't see an appearance of the z variable, so you know this is a cylinder. So in the xy plane, go ahead and draw the ellipse, which is the graph of x squared plus 4y squared equals 16 in 2 dimensions. And then draw a couple other copies of that ellipse above and below the xy plane. And because you know that this is parallel to the z-axis, it's a cylinder, go ahead and draw several of these vertical construction lines to get your surface there, which is, and this surface right here is the graph of that equation there. And by the way, this is an example of an elliptic cylinder because the cross sections, aka traces, are ellipses. This is part B of example 7. A little bit more cryptic here. You have x is equal to sine z because you have an equation that doesn't involve one of the variables. This equation only has x and z in it. So that you know that whatever the graph is, the surface is going to be parallel to the y-axis. So in the xz plane, draw the graph of x equals sine of z, which is the little pink sinusoidal graph right here, and then make a couple other copies of it to the right and to the left of the xz plane, and then draw several lines parallel to the y-axis to connect those sinusoidal curves. And you'll have your surface here, which is the cylindrical shape of x equals sine of z, which is the graph of that function. So we now know what cylinders are. Now let's talk about the general class of surfaces that will almost always involve all three variables. But these will be the three-dimensional analogs of conic sections in 2 dimensions. Remember, your conic sections involve ellipses and hyperbolas and parabolas, and circles and lines and points and stuff. The quadratic surfaces are the three-dimensional analogs of those. And hold on, let me go back. So if you take a look on page 866, it's going to be, at least for the equation, whenever you could write it in the form of ax squared plus by squared plus cz squared, I should say cz squared, plus dxy plus exz plus fyx plus gx plus hy plus iz plus some constant j. If you could take your equation and put it in this form, and of course the highest degree term would be second power. You don't see any square roots or anything, but as long as you put it in this form, then you know the equation will have a quadratic surface as the graph. And there's a whole zoo of these things, a whole. So we're just going to kind of quickly go through the next few pages, and I'll let you look at them, and you'll have the chance to play with these on homework without spending a whole lot of time in class. Here's an example of an ellipsoid. The equation is z equals x squared over 16 plus y squared over 4. That's the equation. Now remember, traces and intercepts. Let me check something out here real quick. Sorry, I got this one wrong. I thought that this looked really weird. Erase that. This has a different equation. I wrote down the equation of a paraboloid, elliptic paraboloid. The equation for this ellipsoid is x squared over 9 plus y squared over 16 plus z squared over 25 is equal to 1. So there. That looks a lot better. I had that probably that little puzzle look on my face. Man, that don't look right. All right. Now, traces. Set z equal to 0. When you set z equal to 0, then you have the ellipse x squared over 9 plus y squared over 16 equals 1. And that's this one now, right here. And likewise, you can find the trace in the YZ plane by setting x equal to 0. If you set x equal to 0, you got this ellipse right here in the YZ plane, which is the green ellipse. You got the blue ellipse here in the XZ plane, where you set the y coordinate equal to 0. So notice how after you created the three traces, you got the general shape of the surface, and then you can go ahead and put the skin on it, so to speak. And there's the skin, there's the surface. There's your generic ellipsoid. Good example, garden variety ellipsoid. All right, this one is your elliptic paraboloid here. So this has the equation z is equal to x squared over 16 plus y squared over 4. Now, let me just mention that if you try to set z equal to 0, then you have 0 equals x squared over 16 plus y squared over 4. And so what do you think x and y are in order for that equation? That x and y would also have to be 0. So that's actually going to be that one and only intercept that you see right down there at the bottom. But for fixed values of z, then you will have ellipses. So if z equals 1, you'll have some ellipse. If z equals 2, you have another ellipse. Z equals 3, you'll have yet another ellipse. So for different positive values for z, you'll have this family of ellipses as traces. Contours, right? Contours. Talk about contours here in a little bit. And then if you were to set x equal to some constant, like 2, for example, or 4. For different values of x, you will have these different equations for parabolas parallel to the YZ plane. So, for example, if you set x equal to 4, 4 squared is 16, then you'll have the parabola z equals 1 plus y squared over 4. The graph of which looks something like pink thing right there. So you can kind of imagine that letting x vary through different constant values, that imagine this pink parabola coming out then going in, and what you'll just be seeing parallel parabolas, vertically oriented. And likewise, you could set y equal to some constant value, and as you adjust the value for y, you'll have a parallel family of parabolas that are parallel to the xz plane, like the blue parabola there. So you have these various traces and contours and stuff that will form the skeleton of your curve, of your surface, I mean. And then you can, of course, put the skin on it and have the graph of your elliptic parabola. Why is it elliptic? Because the cross sections are elliptical, huh? If you were to take a slice that's parallel with the xy plane, that slice would have the shape of an ellipse. In other words, the traces are elliptical in nature. All right, here's a hyperboloid here. For example, number 10, hyperboloid of one sheet, because it would just be composed of one sheet of paper if you could somehow manage to make it involving one just sheet of paper or tinfoil or whatever. Now the equation is actually back here. Here's the equation of this hyperboloid here. X squared over 4 plus y squared over 9 minus z squared. And in general, when you have all three terms involving squares, but one of the terms has a minus in front of it, and the other side of the equation you have a constant like 1, not 0. Some non-zero number. When you have a 1 minus sign, that's going to be hyperboloid of one sheet. 1 minus, one sheet. So how many minuses will a hyperboloid of 2 sheets have? 2. There you go. Good. See, we're all mathematicians. We observe patterns, right? Now, we don't have a hyperboloid of 3 sheets, though. Sorry. So, but anyway, so you saw this equation right here, right? And then you go through the same process. You want to sketch the graph of it? Well, look at the traces in the xy plane by setting z equal to 0. It says z equal to 0. You have x squared over 4 plus y squared over 9 equals 1. That's an ellipse. You can set z equal to some other values, some other constant values below, negative and positive. The result of which will give you an equation of some other ellipses. So this green ellipse down here is where you have z equals some negative number like -2. Up here you have this green ellipse where you have z set equal to some positive value like +2. Then you have the other traces where you set maybe y equal to 0. When you set y equal to 0, when you have y equal to 0, then you have a hyperbola, huh? You got the 2 branches of a hyperbola. And you said x equal to 0, you got a hyperbola. That's why they call it a hyperboloid. Okay, so go ahead and take a look at that. Moving on here. This is example 11, a hyperbolic paraboloid. Hyperbolic paraboloid. This has the equation of z is equal to x squared minus y squared over 4. So again, you can make sense of if you were just given the equation and you don't know what the graph looks like. Again, set z equal to 0, figure out what y and x, well, x and y would have to be both 0 in order to satisfy that, z being equal to 0. But for other values of z, you would have hyperbolas, right? So if z is positive, you'd have hyperbolas that look like this. For negative values for z, you'll have hyperbolas that look like this. Maybe you can set x equal to 0. If you have x equal to 0, then you have a family of parabola. Z equals negative y squared over 4, which is the blue parabola that goes down. If you set y equal to 0, set y equal to 0, then you have z equals x squared, which is that pink parabola. So this shape right here, in fact, this region right here is called a saddle for obvious reasons. Which is interesting. We'll have some experience with saddles later on in the course. But imagine me asking you the question is, if you're standing right here on the saddle, is that a maximum or a minimum value? And your response would be, well, it depends on what direction that we're talking about. With respect to the XZ plane, then it's minimum. But with respect to the YZ plane, it's a maximum. But in general, it's neither. We will talk about finding maxima and minima of multivariable functions, but also there's saddle points as well. And that's an example of a saddle point. And this is an example of a hyperbolic paraboloid, because the cross sections are hyperbolas. An example of an elliptic cone. This has the equation y squared over 4 plus z squared equals 4x squared. Or if you were to bring the x squared over to the left, you'd have a y squared over 4 plus z squared minus 4x squared equals 0. So again, if you look at traces, maybe you could set z equal to 0. And if z is equal to 0, then you have y squared over 4 equals 4x squared, which will give you 2 lines. Like those 2 pink lines. And for different values of z, you will have different lines. If you were to set x equal to 0, then you would have y squared over 4 plus z squared equals 0, which means x and z would both have to be 0. So it shouldn't be a surprise that you have the one intercept right there at origin. If you were to set x equal to some non-zero constant values, then you would have families of ellipses. Like for example, for this green ellipse here, you have some x. You have x equal to some positive value, like 2 or something. You set z equal to some constant value. And what would you have? You would have a family of hyperbolas, maybe. So think about when you're given these curves, these equations, and you have to graph them. Think about, what do you get when you set one of the variables equal to 0 or to some other constant, and do that for each of the variables. Here we've got an example of a hyperboloid of 2 sheets. And notice indeed that we've got 2 minuses. In this example, we have a minus in front of the x squared term, we have a minus in front of the y squared term, and a plus in front of the z squared term. So it shouldn't be a surprise that this hyperboloid is oriented opening upward and opening downward relative to the z-axis. For example, and notice that the x center is displaced by 2 units. because it was turned. And we can go through the same discussion by letting x, y, and z in turn be equal to 0 or some constant values. All right, moving along here. So you see at the back of section 13.1, you have this table of these quadratic surfaces that we've talked about. This is just a summary here of the general equations of what the equations will look like. Okay, you'll have the chance to play with these in the homework, though. So we have the ellipsoid. So remember what the equation of an ellipse is. This is the three-dimensional version of it. The orientation of it, meaning the longest part of it, where you have the major axis, is determined by which of these x, y, or z terms have the largest denominator. There's your elliptical or elliptic paraboloid here with this form of the equation here. Of course, you can swap the x with the y or the y with the z or whatever. So you could have your paraboloid oriented along the x-axis, along the y-axis, or even at some angle if you want to, but that's just the general form. We talked about the hyperboloid of one sheet up there, hyperboloid of two sheets. How many minuses does the hyperboloid of one sheet have? One for the two sheets? Two? All right. So what to look for. So when I test on this section or on this chapter, I might give you a matching part. I might give you like 5 graphs or 5 surfaces with 5 equations, and you're supposed to match, right? So I'm sure that you could do that. All right. We talked about the elliptic cones, hyperbolic paraboloid. All right, so just make sure that you're somewhat familiar, even though you don't really have to memorize these, because you can discern what the shapes would be just by thinking about traces and contours. All right, now let's move on to the next section here where we're talking about graphs of multivariable functions. And along the way, we'll talk about level curves and contours. Now, a two-variable function, meaning a function with 2 independent variables. We will usually use z as our dependent variable as a function of x and y. X and y being our independent variables. But we could have the same discussion with y being a function of x and z, or x is a function of y and z. But generally speaking, just as in algebra, when we usually use y as our dependent variable and x as our independent variable, we'll use that same sort of standard setting, so to speak, where we'll have z as our dependent variable, x and y as our set of independent variables. We can also talk about domains in the same sense that we did for the single variable equation. Remember that the domain is the set of allowable inputs into the function. Now for single variable functions, it was usually pretty easy to figure out what the domain is. It's usually going to be where we just omit the values of x, would make your square root become where you would have the radicand be a negative, for example, or if you had a fraction where the denominator is equal to 0 and so forth. Well, it's the same sort of discussion here. We're not going to take square roots of negative numbers. We're not going to take division by 0 and that sort of thing. So we'll have that same sort of sense of figuring out what's in the domain and what's not in the domain, right? In particular, you need to visualize two-dimensional plots of real estate on the xy plane as the domain and values of x, intervals on the, not x but z, intervals on the z-axis as the range of your two-variable function. Here's how you can envision that domain and the range. The domain is some piece of real estate, two-dimensional real estate on the xy plane, and the range is some interval on the z-axis. It could be that that surface goes all the way from positive infinity down to negative infinity. So z would consist of, or the range consists of all real numbers. The range would be in one dimension, the domain would be in two dimensions. It could be that the domain is the set of all values of x and all values for y. Or it could be that it's just right along some line, or maybe it's exclude a line on the xy plane, maybe it's a half plane, maybe it's some circle or disk or whatever on the xy plane. Let's do an example real quick. This is example 1. Suppose that we've got z, which is a function of x and y, so g of x, y. So this is the common functional notation that we'll use for a two-variable function, g of x, y, f of x, y, h of x, y, whatever, and then we have square root of 4 minus x squared minus y squared. Let's find the domain, the largest set of values of x and y, which will form the set of allowable inputs for this function. Of course, we are never going to take the square root of negative numbers and still expect to have real numbers to talk about. So to talk about the set of allowable inputs, we will say that the radicand, which is 4 minus x squared minus y squared, set that to be greater than or equal to 0. Because after all, we can take the square root of 0, and we can take the square root of any positive number. We just cannot take the square root of any negative number. So if 4 minus x squared minus y squared is greater than or equal to 0, that means that 4 is greater than or equal to x squared plus y squared. In other words, x squared plus y squared less than or equal to 2 squared. So we're talking about a disk on the xy plane of radius 2. So that would be the domain of that function. Does that make sense? As long as you are on that disk or even on the boundary, then you're in the domain. But the minute that you step out that boundary, then that function is undefined. Here's a better picture of that domain. Disk of radius 2. Centered at the origin. So when we think about the graph of z as a function of x and y, f of x, y, what's the graph? Well, the graph, frankly speaking, is going to be nothing more than a surface. Just like the graph of y as a function of x is some curve. surface as the graph of a two-variable function. So you roam around the domain of the function, and for each point on the domain, you'll have the x coordinate and the y coordinate. That you'll plug the value for x in, you plug in the value for y into whatever the two-variable function is, and out pops the value for z. And that value for z will be the z coordinate above or below the xy plane. And that collection of z coordinates resulting from roaming around the domain will form the surface, aka the graph of the function. Remember the vertical line test from algebra? If the graph at any point hits a vertical line at two or more places, then the graph is not the graph of a function. And same will apply here. The ellipsoid is not the graph of a function. Remember what a function is? For each input, meaning for our new case here, for each value, value for x and y, there is one and only one output, z. But for the ellipsoid, apparently there will be two values of z for any given ordered pair x, y. So the ellipsoid is not the graph of a function, but the elliptic paraboloid would pass the vertical line test, because everywhere you move that vertical line, that line that's parallel with the z-axis, it only hits the graph once. All right, let's take a look at example 2. Now, I'm not going to write anything down for this, but we have f of xy equals 2x plus 3y minus 12. So we have this function here. Is it a function really? Well, if we could plot the graph of it, and of course the yellow plane that you can kind of see almost edge on, and then imagine that you had this vertical line, this line that's parallel with the z-axis, and everywhere you pass it around, it only hits the graph once. So yeah, z really is a function of x and y for this. What is the domain of this function? Are there any restrictions on x or on y? Or can x and y be any real number? As far as I could tell, x could be anything, y could be anything. So the domain for this function would be all of the real plane, all of R2, for example. By the way, when we talk about the set of real numbers, just a piece of notation, we like to use this blackboard R. This is our way of saying boldface R, which is the name of the set of real numbers. So if I were to go like this, that means that we have the entire plane, the entire xy plane. So R2 would be the domain, okay, for this function. How would we graph this? If we didn't know that this was the graph, how could we graph this? Well, again, by traces and intercepts, right? You could set z and x equal to 0, solve for y, and so forth. And so plot the intercepts, plot the traces, and then you don't even need to hit the traces as long, because you know that for a plane that the traces are going to be straight lines in between the intercepts anyway. So as long as you hit the x, y, and z intercepts, then you can kind of draw the line segments between those three intercepts. And then imagine that you have the plane that goes through those three intercepts. Okay. This is example 2b. You have z is equal to x squared plus y squared. What would be the domain for this function? The set of allowable inputs for x and y? And the short answer is all of R2, because there aren't any restrictions in x and y. And we know how to sketch the paraboloid because we can set z to any non-negative quantity, and you would have a family of circles in this case. Moving along here. For this function here, z equals square root of 1 plus x squared plus y squared. What is the domain? Well, we know that we cannot take the square root of a negative number, so we would set 1 plus x squared plus y squared to be greater than or equal to 0, right? And then x squared plus y squared greater than or equal to negative 1. But regardless of what x is and regardless of what y is, x squared plus y squared is always going to be at least 0. So still, for this particular function, all of R2 would be the domain. Okay. Moving along here. Now, who likes to hike? Who's familiar with the contour map or topographic map? So when we're talking about rocky terrain that has variable elevation, we could take a look at a topographic map and get some information. What a topographic map, here's an extract of a topo map, is that for fixed elevations you have a curve. So for example, for elevation of 6,400 feet, then you would follow this curve right here. So imagine a trail going through the hills here that is exactly elevation 6,400 feet. And that would be this curve right here. And then, so you have to then decide if you go up, which way would you be facing, left or right? So if you're standing right here at the contour at 6,400, which way would you have to face in order to go uphill versus downhill? And usually it's pretty easy to figure out by taking a look at the next contour line, bold line. If it's at a higher value, that means that you go uphill and going in that direction. And indeed, you got 6,400 feet here, and over here you've got 7,000 feet. So, okay, that means that going uphill means going this way. Now, you'll then look at how close are those contour lines to each other. If they're really close to each other, that means that you're going uphill more quickly, that the terrain is more steep. Versus if the contour lines are more stretched out, further apart from each other, like down here, that means that the terrain, meaning the elevation, is changing more slowly. Well, we can use contours with our graphs or curves. Remember, when you have z of some function of x and y, we can set z equal to some different integers like 1, 2, 3, 4, 5, 6, 7, and figure out what the resulting equation would be involving x and y, and project those curves down onto the xy plane. For each different constant value of z, you will have a level curve where you have x and y as a function, at x and y equal to some constant. So you could have z equals x squared plus y squared, but you can set z equal to 0, and you'd have the level curve, which is the dot right on the xy plane at the origin. But if you had, so you have z is equal to x squared plus y squared. If you set z equal to some constant like 1, then you'd have the level curve of a circle of radius 1. If you had z equals 2, then you'd have a circle of radius square root of 2, and so forth. If you have z equals z naught, or some constant, then you'd have a circle of radius square root of z naught. Now the contour curve up there on the curve for a fixed value for z, that's your contour curve, worth the loop. Fixed value for z, which is the distance above the xy plane. But when you project that contour curve onto the xy plane, that's what we call the level curve. So we may not have a really good sense of what the curve would look like in 3 dimensions, but if we set z to some different values, some different constant values, and figure out what those curves look like on the xy plane, then we can get some sense as to how that curve evolves over the plane. So, for example, we might have this surface here intersected at some different values for z. Those are some contour lines, some contour curves over there. This is what those will look like as level curves. Remember, level curves live on the xy plane. Here on the curve, we have our contours. If we were to shine a flashlight straight down, pointing toward the negative z direction, then the shadows of those contours would look like this on the xy plane. So this is the only information that we've got, and we can't see this surface over here. We can at least imagine that maybe there's some sort of dip or some dome, which would be the shape of the surface. That's the information that we get from the level curves. And again, if the level curves bunch up, like right here, we could tell that the elevation of your surface is changing much more rapidly than if the level curves were more spread apart, like right here. So we can see that when we go in this direction, that there's more rapid change in elevation on the surface compared to here where it's relatively shallow. Okay, just like reading a topo map. Here's a equation z equals y minus x squared minus 1. Set z equal to some different constant values like z equals -2, z equals -1, z equals 0, z equals 1. And for those different values of z, then you'll have these different equations involving y and x, whose curves appear right here on the xy plane. So this will give you some information as to what the surface looks like. And of course, as z increases in value, you know that the elevation is going to be increasing for these increasing values for z. So as these level curves go this way on the xy plane, that you know that the elevation is increasing in the z-axis. And indeed, put all that information together and here's your surface. Is this making sense, kind of? Here's example 3b, where you've got z equals e to the negative x squared minus y squared. So again, set z equals some different constant values. And of course, the resulting would be a family of circles. Because remember, if z is equal to some constant, like for example, a half, if z is equal to a half, then what would we have? Take natural log of both sides. You have negative natural log of 2 is equal to negative x squared minus y squared. So you would have x squared plus y squared is equal to natural log of 2, which is just some number. So the level curve would just be a circle centered at the origin, a radius the square root of natural log of 2, for example. So, but for each different value of z, you would have a different level curve of a circle centered at the origin with a certain radius. And then you could piece together, based on these different values of z and these different concentric circles, what the shape of the surface will look like. Now, if x and y were both 0, then you'd have z equals 1. So you can see that the maximum value of this function would be 1 at 0, 0. We'll talk about our two-dimensional or a multivariable calculus, how to actually find our maximum and minimum in general for our multivariable functions. Here's yet another function that's interesting. We have z equals 2 plus the sine of x minus y, so another perfectly good two-variable function. So what does this look like? So what do the level curves look like? Because we are not going to be given a surface. This is just what the surface happens to look like. But how could we get that? Well, again, set z equal to some different number. Now, we know from the context of the problem that z couldn't possibly be 4 or negative 6 or whatever, because we know that the sine function varies between negative 1 and positive 1. So that means that z can never be less than 1 nor greater than 3. So we can set z to some different constant values between 1 and 3, and then subtract 2, and then take the arc sine. And so whatever the arc sine of z minus 2 is, then you'll have x minus y equal to that constant value, which will produce this family of lines. So z alternates between 1 and 3 with these level curves that are straight lines. So that's what gives us the inspiration that we have this ripple sort of surface for the graph of that function. Okay. Here's yet another interesting function. Anybody think about going into statistics as a major or second major or anything? Well, here we've got a probability function. Probability, remember, is some value between the 0 and 1, which will indicate the likelihood of some event happening, with 0 meaning it's not going to happen, and 1 meaning it's going to happen with 100% certainty. And then anywhere in between, of course, will indicate the likelihood. Probability of 0.5 means 0.5, 50-50 chance, etc. As in, it's going to be about a 50-50 chance that we'll have a significant storm tonight, right? Between midnight and 6. Right? But example 5 has to do with, okay, there's a certain fraction of people on campus that have a certain infection. And suppose that you're going to bump into n number of people during the course of the day, and then this. So R is the fraction of people that have the infection, N is the number of people that you bump into, and then P will calculate the probability that you yourself are going to get that infection. So suppose that maybe half the people in campus have the infection, and you bump into 10 people. So 1 minus a half is a half. A half raised to the 10th power is some rather small number. 1 minus that will be some number that's close to 1. So it'll be almost certain that you get the infection yourself, for example. So what is the graph of this two-variable function? After all, P is a function of both R and N. That probability is a function of the fraction of students who have the infection and the number of actions that you will have with the students on campus. So why should we believe that this curve, this surface right here is the graph of that? Well, you could set P equal to some different constant values. Like, for example, if P is equal to point A, then you can graph R versus N for these different values for P. So what we have here are some level curves. Now, this two-variable function P is only defined for positive values for N and for R between 0 and 1. Does that make sense? So the domain of this function will be where R is between 0 and 1 and N is non-negative. P being a probability, we should expect that the range for this function to be between 0 and 1. Does that make sense? Meaning the set of real number outputs for this function between 0 and 1. So for these set of families of level curves, you see how that kind of corresponds to this. You have the R-axis there, here's the R-axis. Here's the N-axis, corresponds to this N-axis. And the further that you go away from the origin, so for larger values of R, larger values of N, P is going to get closer and closer to 1. And that's indeed what we see here. Okay. So the higher the fraction of students that have the infection and the larger number of interactions that you have with the students, the higher the probability that you yourself are going to get infected. And another way that you could actually figure out what the surface looks like is to actually kind of complete a grid right here. So you know that in some, sequence or of real numbers, now really N is going to be non-negative integers, right? So you could write a whole bunch of them down like we did right here. And for R, some reasonable values for the fraction of students that have the infection. And then input the value for N, that value for R into the function, evaluate it to give you that probability. So this tells you that if there are 3/10 of the students, 30% of the students that have the infection, and you have 5 interactions, there's an 83% chance that you yourself will have the infection. But of course, notice that by the time that you get down here where you have, a large enough fraction and a large enough number of interactions, that your probability is essentially 1, that 100% chance of getting the infection. So then imagine what the surface looks like. It's going to be relatively small, but down here. But as we get out here, it's going to be basically plateauing with a height of 1 out in this direction. Okay. So another way of thinking about what the surface looks like. Here's yet another example. This is example number 6 for those people who are the electrical engineer students here. All right. Electrical potential function. Let me go and write the function down. So we have phi of x comma y is equal to 2 divided by the square root of x squared plus y squared plus 2 divided by the square root of x minus 1 squared plus y squared. Now, notice right away that you're going to have 2 points at which the domain that are not going to be in the domain for this function. For this first fraction, that denominator is going to be 0 at 0 comma 0. In the second fraction, the denominator is 0 at 1 comma 0. So it shouldn't be a surprise that you don't see anything on the plane there for the level curves. So you can, what some people do is just put a big black mark on that little hole. And then for fixed values of phi, positive values, then you can figure out some appropriate shapes for x and y. Not very easy, mind you, but you can use computer or a calculator to plot those curves for the different values, fixed values for phi. And those what the level curves look like here. And here's what the surface looks like. Of course, the closer and closer that you get to 0, 0, or 1, 0 on the plane, the higher magnitude that phi is going to be. But of course, once you get on top of those 2 points, either one of those, then you go to infinity. The function's not even defined there. All right, moving along here. We're almost done with this, and we'll take a break and take our quiz. So we were familiar with our one variable function, but our two variable function we have v as a function of x and y. But if we have a function of 3 variables, then we'll use w typically as a function of x, y, and z. Hey, we can even have an invariable function. And when we go beyond 3 variables, we will typically just use subscripts as an x of 1, x of 2, x of 3, x of 4, dot, 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 x of n as our invariable function. We didn't really talk too much about the implicit form, but if you have y as a function of x, you can always move the y over the other side of the equation, so you have some function of x and y being set equal to 0. Well, we could do the same thing with our 2 variable function where we move the z variable over to the other side of the equation, so then you have a function of 3 variables set equal to 0, what we call the implicit form. We have a lot more to say about the implicit form. But that's what the implicit forms look like, where the capital F would be that function of the involving that extra z variable or w variable or whatever. Okay, so that's that. So the discussion that we had for the 1 variable function, the 2 variable function, and so forth applies for the invariable function. No matter how many independent variables that you have, the domain is still the set of allowable inputs. And the range is going to be the set, basically the interval of outputs. Okay, as you go over the domain. So let's do a quick example of a higher order function, and we should be just about done. Example 7 here, we've got g of x, y, z, so a function of 3 variables. This happens to be the square root of 16 minus x squared minus y squared minus z squared. What is the domain of this function? Okay, set the radicand of 16 minus x squared minus y squared minus z squared. Set that to be greater than or equal to 0. And then figure out what you need to do to figure out what the domain is in 3 dimensions here. And as a matter of fact, if you add the x squared plus y squared plus z squared over to the right hand side, you have x squared plus y squared plus z squared, which is less than or equal to 16. And folks, what we're talking about here is a sphere, a solid sphere of radius 4 centered at the origin. That would be the domain for this 3 variable function. Now the graph would be a four-dimensional surface, which we don't know how to draw. We can gain information about what that four-dimensional surface would look like by setting G equal to some different constant values and have a sequence of level surfaces. Let's take a look at B here. We've got H of x, y, z is equal to 12y squared over z minus y. All right, we have a fraction. We know that we cannot divide by 0, so that means that you set z minus y equal to 0. And so that we know that as long as e minus y is not equal to 0, then we have the domain. But wherever z minus y is equal to 0, we will exclude that set of points from the domain. But we know that we're operating in 3 dimensions, don't we? So we're talking about the plane defined by y equals z is not in the domain. So one way that we can express the domain is in set builder notation. Maybe we could write it like this: x, y, z such that y is not equal to z. That would be our domain. Okay. So we talked about level surfaces, right? That's where if you have a function of 3 variables, and I told you that the graph is a 4-dimensional surface, which we can't even visualize because all we know how to visualize is in 3 dimensions. Huh? But you could set W, the dependent variable, equal to some different constant values. So for example, if you have W is equal to the square root of z minus x squared minus 2y squared, and then you set W equal to 0, for example, then if W is equal to 0, then you'd have z minus x squared minus 2y squared equal to 0. So which would give you z equals x squared plus 2y squared, which is a parabola. Then set W equal to 1, and then you would have a different paraboloid. Set W equal to 2, and you'd have yet a different paraboloid with the vertex of 2 units, and so forth. But exactly what this would look like in 4 dimensions, I couldn't tell you. But at least you know what the level surface is. So if you can imagine the relationship between level curves and the surface graph of the function, then that's going to be the same relationship between the level surfaces for your 3-variable function and its 4-dimensional graph. Okay? This right here would be a picture maybe of temperature as a function of the 3-dimensional location on a solid object. There's one way of visualizing what a 4-dimensional graph would look like, where you have the different colors at the different locations in space. All right. So anyway, that's it for that. Okay, so we're done with the material. So if you want to take a quick break, that's fine. Otherwise, I'll pass out the quiz, and you can use the rest of the class period to do it. And let me go ahead and stop recording here.